Hello, everyone. My name is Glenn Abilie. This is my final project presentation for CSCI 89B Natural Language Processing. This project is a case study in topic modeling with focus on aviation safety. A quick introduction about myself in this project. I have 20 years of aerospace experience as a structural engineer. I've witnessed firsthand the positive impact of improved safety measures. My motivation is simply safety is paramount. I want my family, my friends, and my community safe when they fly. I will be applying a data-driven approach, leveraging analytical methods on 15 years of incident to uncover recurring failure types and their contributing factors. So for the problem statement, let's start with the data challenge. Aviation incident narratives hold key safety insights. But the problem is their unstructured format complicates this systemic analysis. The key problem is how can we analyze these narratives to extract recurring themes, understand causes, and track trends over time? The approach that I will employ is structural topic modeling on NTSB reports to categorize major themes. And the research questions that I would like to ask are one, what are the main incident categories? Two, how have incident types evolved over 15 years? And finally, what are the most common underlying causes? The outcome I hope to gain is generate insights that, using my domain knowledge, can guide safer aircraft designs, improved maintenance, and more effective operational procedures. The dataset is a publicly available file from the NTSB website. You can see here the website. It is basically 500 megabyte file in Microsoft MDB format. The extracted narrative from this 500 megabyte file is about 38 megabyte file in size. So this 38 megabyte file contains observations of about 20,000 aviation incident narratives. It ranges from the year 2008 to 2024 and has about an average character length of 5,600. The content of each narratives are the following. It has preliminary narratives, which is the initial report, the final narrative, which is the in-depth post-investigation detail, the identified causes, and the incident dates. I've included a sample here picture to have an understanding of what it looks like. For technology and methods, I'm using R programming within RStudio. My machine configuration is an Intel Core i9 processor with 64 gigabyte RAM, 64-bit operating system with Windows 11 Pro. I'm using structural topic modeling, of course, with the following libraries: OpenXLS for importing Excel, deploy-R for manipulating and transforming data, ggplot and wordcloud for visualization, the STM package itself, of course, tidyr for manipulating data frames, random for reproducibility, and because I'm colorblind, I'm using Viridis color palette. I basically took 5 steps. The first one is data collection and preparation. This is where basically I imported the narratives and pre-processed it. The second step was the EDA, exploratory data analysis, where I created bar charts of incidents over time. The third item is basically the structural topic modeling, where I identified 2 models. One is over time in years, and the other one is seasonality, such as winter, spring, or fall. The fourth step that I took was the interpretation of the structural topic modeling results. And then finally, I created a report with a bunch of visualization for this project. Now for the first step, data collection and preparation, this is where I loaded the data. I selected columns. Not all the columns were used in this project. And then I cleaned those information, combined some of them into one narrative. I extracted the date and reformatted it. I created seasons out of these dates. I extracted some sample since Canvas can only take 10 megabytes as a requirement for this project. And then I did text preprocessing and finally prepared the process text for STM analysis. Now for the EDA, after pre-processing, I have 19,860 observations with 11 variables. The key variables that I use in this analysis are simply the NAR combination, the date, and the season. Now the NAR combination is simply the combination of these three info pieces of information. The date comes from the EVDI, which has a date information within it with some extra strings, and the season from the date, which is basically 4 categorical variables, which is winter, spring, summer, and fall. The second part to the EDA are basically 3 bar charts. The first one is incidents over time or by year, incidents by month, and incidents by season. Incidents by season is basically the incidents by month, except it's aggregated by about 3 months. For example, the summer season is June, July, and August. The winter season is December, January, and February. So you see that correlation, and that's really simply the reason why. Now, observations on the incidents over time, you can see 8 as the peak ones, and there's a general trend coming down. You can see here, starting in 2020, there's a big drop in incidents. That's mainly because of COVID-19, where most aircrafts are grounded and people are restricted from traveling or flying. The other observation here is 2023 and 24 lacked a lot of data, and that's mainly because some of the investigations are still ongoing, so it's not included in this analysis. With all these pieces of information, I am looking at two structural topic modeling. One is over time or by year, and the other one is by season. For the STM, there are simply two important codes that I used, important functions. That's the search K function and the select model function. The search K is to find the optimal number of topics. So you can see here I searched up to 30, from a 3 to 30, and using date as a preference. Now for the select model, once I selected the most appropriate K, which in this case is 8, on the select model function, I use the prevalence of date, similar to the search K, and runs up to 25. You can see here, this is the date, which is in years. Now for the STM over time results, I have about 7 charts here that I will explain. First one is the likelihood. The positive slope starts to decrease around K10, suggesting that this model's ability to predict unseen data improves less significantly beyond this point. For the residual, it shows a steady decline, but the rate of this reduction slows around K10 as well. This suggests that the proportion of unexplained variance becomes minimal beyond this range. For the semantic coherence, and probably better to use this chart for the semantic coherence, we can see here beyond 8, which is this line, and we can see a significant drop in coherence. For the lower bound, it shows a steady increase, but the rate of improvement slows down after 10. This also suggests that the model achieves a better fit to the data up to this value and has a diminishing improvements beyond K10. Now, for the trade-off between exclusivity and semantic coherence, we see that 7, 8 to maybe about 13 is where we have a good trade-off between the two scores. As you go beyond 13 or 11, you see a significant drop in coherence, while if you go below 7 or 8, you'll see a significant drop in exclusivity. Now, going into the composite score, let me explain first why I use this two factors here. Since I'm very interested in coherence, I put a little bit more weight on coherence here, which means it's 70-30 instead of the 50-50. So for the composite score, this is the scoring that I created. And we can see here, 8 is the best score so far. So we're going to be using the optimal K8 value for the search after the search K. Now for the select model, I've ran that function and saw that 5 is the best run. And as you know, as you get to the upper right corner, you get the best results, the best semantic coherence and the exclusivity scores. So I use 5 as the optimal run for K. Now, using the output of the selected model summary, such as the highest probability, frequency, exclusivity, lift, score, top documents output, I was able to determine a short description for each of the topic. And these are all the short descriptions of the 8 topics. On the prevalent chart, you see topics 8, 1, and 7 are the most prevalent. And these are landing and ground handling, light aircraft and gliders, and fuel and power loss. Now, looking at this chart, effective incidence year on topics. So you will see here pretty much everything stable or declining except for one chart right here, which is number 6, runway and traffic incidents. That needs to be taken a look at in detail. Now for the result interpretation of trends over time, the key topic findings, as I mentioned earlier, are the landing and ground handling, the light aircraft and gliders, and finally the fuel and power lost. For the temporal trend, the most concerning one is the runway traffic incidents. That's basically increasing over time, which we need to watch out. Now, as a recommendation for these key topic findings and the temporal trends, the regulators should look into runway safety and better weather forecasting. And then operators should adopt advanced maintenance and improve fuel management practices. Manufacturers, on the other hand, should enhance landing systems, improve designs for small aircrafts and helicopters. And then finally, the actionable steps that they can take are 1, training, address disorientation like crosswinds and fuel management. Technology, invest in predictive maintenance and weather forecasting tools. And then finally, the process improvement, strengthen runway ground traffic management. So the functions and parameters used in the STM by seasonality is pretty much the same as the STM by overtime. The only difference is really the season. So you can see here we have a prevalent season and prevalent season right here. And that's mainly because we're looking at these 4 values right here: winter, spring, summer, and fall. So we also have 7 charts for STM by seasonality. So the first one right here is the likelihood. We can see 10, beyond 10, there's a diminishing return in the likelihood. The same as residuals, beyond 10, you don't get as much benefit. For the lower bound, similarly, 10 is also a diminishing return beyond that. Now for the coherence, we can see here the coherence charts as well. we can see beyond 7, it starts to drop, and then beyond 9, significant drop. Now, for the trade-off between coherence and exclusivity, we can see here between 7 to about 13, where we get a good range of good scores between trade-off bounds between coherence and exclusivity. Below 7, you get less exclusivity. Below 13 or 12, you get lower coherence. Now, with that, given that information, we go into the composite score. Again, once again, 7, I put a little bit more weight on coherence than exclusivity because I'm more interested in coherence in this study. So with that, we can see 7 as the highest score. Between 7, 8, and 9 would be good K values. Now, finally, I've decided with all these charts, I've decided the optimal K for SDM by seasonality is 7. Now, once I ran that information, I used the select model, and we can see in the select model results that the upper right corner shows that 5 has the best value. So using optimal run of 5. Once again, using the output selected model summary, I was able to determine a short description of each of the topics right here. Most of them overlaps with the previous SDM, except for landing gear failures. This is a new topic for seasonality. The most prevalent topics are 7, 6, and 4, and the 7, 6, and 4 is basically landing, runway operations, light aircraft, and training incidents, fuel, and engine failures. By the way, these are also the same most prevalent topics in the SDM by year. Now, moving on to the seasonality, effect of seasonality between summer months and winter months, we can see here as light aircraft and training and the landing and runway operation incidents appear to be more prevalent in the summer months, while on the opposite side, we have weather-related incidents appear more prevalent in the winter months. Very interesting. So the results for seasonality. So the key topic findings are landing and runway operations, light aircraft and training, and fuel and engine failures. The seasonal patterns are training incidents correlate with warmer seasons and increased flight activity. There's a spike in weather-related issues during winter months. Fuel and engine failures remain steady regardless of the season. For operational improvements, landing and runway, enhanced braking systems and runway upkeep. For the fuel and engine, manage fuel freezing during the winter and vapor lock during the summer. For training, tailor safety modules to peak training seasons. And then for the weather, invest in advanced weather prediction and radar systems. So in conclusion, I was able to answer my research questions. Number one, the main incident categories. I found 8 primary topics or categories with 3 particularly prevalent areas: the landing and runway operations, reflecting the challenges in approach landing and taxiing phases; light aircraft and training incidents, highlighting the role of pilot preparedness and proficiency, especially with smaller and specialized aircrafts; and finally, the fuel engine failures. This underscores maintenance, inspection, and technical reliability issues. For my second question, the evolution over 15 years. Incident categories are generally stable or show signs of improvement over time. It's reflected in the light aircraft and runway handling over time. However, a subtle increase in runway and traffic incidents suggests emerging complexities that are present in the air traffic management and operational condition. Seasonal effects are evident. We saw that. And with weather-related challenges and training incidents peaking during specific times of the year, this indicates the environmental conditions and seasonal activities play a big role in all these incidents. Then finally, to my last question, the common underlying causes. Persistent underlying factors span 3 key domains. I identified 3 key domains. First one is training. Ensure the pilots are, and especially those operating light and specialized aircraft, should receive adequate and timely instruction. Technology investment, advancement in predictive maintenance systems, reliable engine components, and sophisticated weather forecasting tools can mitigate core technical and environmental risks. Then finally, process improvements, stronger operational controls, particularly around runway usage, traffic management, and fuel system checks are crucial to reducing incidents, frequency, and severity. So for what worked and didn't work, initially I used the final narrative, but incorporating all the narratives actually helped me understand the topic themselves. So that's what I did moving forward. The second item is sparse user data. There was a user column variable, but it only had 4,500 observations. So that didn't work. So now I excluded that. Initially, I used a maximum of 50 instead of 30. That took a lot of time, and I reduced that to 30, which still had a very similar result. It didn't impact all my analyses. And then large data set challenges. I was using, every time I coded in and run the model, I was using the entire data set, but I realized I should have taken a subset of that for testing out my codes to make it more efficient. So that's what I did. And then finally, the seasonal topic interpretation. I was using the default value for that for the charts, and it wasn't very clear. So I used custom topic labels, which helped me understand my charts better.